Okay, folks, we're about to get started. Good morning, everybody. Welcome to day 9 of the US QIS Summer School. We are getting very close to the end of the school, so I want to do a few announcements to prepare you for that. Though first, let me give you a summary of today. We will start off with our morning lecture. I'll introduce our speaker in just a moment, but we'll have our break after this lecture, and then we're going to have a presentation on educational opportunities. And this is one of the top questions that I've received over the last 2 weeks is how do I get connected with the national laboratories and the internship programs that are available there. So whether you are in undergraduate, graduate, postdoc, all levels of educational development, there are multiple programs. And so we'll have someone come in and talk to you about that. That's a change from our schedule. We had expected Joe Carlson to be here, but he wasn't able to join us today. So we'll have this presentation instead. We will then have our lunch break. And then immediately after lunch break will be final classes. So this will be the last afternoon session where we have classes, because tomorrow, which will be the last day of the summer school, we will not have classes in the afternoon. We'll only have our morning closing session. We'll have a speaker from next year's summer school host, the Quantum Systems Accelerator, come in and talk about that. Now, in terms of tomorrow morning, when you leave the residence hall, for those of you in the residence hall, you need to take everything with you. You are not coming back, and they are not keeping anything for you. So anything you brought needs to leave your room. Be sure to pack your bags. You'll load your bags onto the buses. You will keep your bags onto the buses when you get here. So you do not have to unload the buses when you get here. The buses will stay around. When we dismiss the summer school, which will be about 11:30, that's when the buses are going to leave. Let me restate that. We'll dismiss the summer school about 11 o'clock. So that will give you time to get on the buses, which will leave at 11:30. They'll leave at 11:30 to go to the airport. They'll get to the airport around 12:30. At that point, you'll take all your baggage off the buses and then take your next step going home. If you are not riding the buses, you are responsible for taking your baggage and getting yourself here in the morning. So there are a few people who have cars. Several people want to carpool with them. That's absolutely fine, but you are entirely responsible for carrying your baggage and getting yourselves here. So you cannot put baggages on the bus if you're not riding the bus. So keep that in mind when you're thinking about how many people can I put in my car. In addition, yes, please, Mary. That's right. Yeah, Miriam, exactly right. You're special case. So you'll be on the bus when you come here in the morning. You will want to take your things off the bus when you get here, but just Miriam. It's a very small airport. You'll be dropped off at the departure station. So basically you pull up to the front doors and you get off and yeah, immediately go into the airport. So very short walk. Get off the same bus when you leave here. That's exactly right, Kevin. So take a look at which bus driver you have. They'll be in that same bus when you get on there. Yeah, check in with Teresa. She can make sure you understand where to park. That's actually the tricky bit if you're driving a car here is that you have to park in the parking lot that's to the north of the traffic circle. So you may remember when the bus comes in, it goes about a big circle. The first right is that North Conference parking lot. It fills up very quickly. So I strongly advise you be here by 8:30, which means you're leaving about the same time the bus is. Okay, so if you are driving, I recommend you leave about the same time as the bus, 7:30 or so, to ensure that you can get through the gate, that you can get to the parking lot, you can find a parking space, and it's a 5-10 minute walk over here. Now, when we dismiss, we will have boxed lunches available. So if you're taking the bus or you're driving a car or whatever you're doing, we'll have lunch available for you, but it'll be the kind of lunch that you can take with you. So we can get you out of here into the airport as soon as possible. Okay, I think that's everything. Teresa, did I miss anything? Okay. Any other questions? Okay, one other announcement about what's up on the screen right now. So we have created a website. You can see the link at the top. This is the QR code. If you scan that with your camera app and click the button, it'll take you to the website. This is a survey where we'd like to get your feedback on the school, both in terms of its content as well as how we operated and executed things. In addition, there's lots of questions there about demographics. That's because Department of Energy wants to do a survey and understand, well, what community is the summer school actually serving? Some of this is about what's your field of interest, what are your aspirations, what's the level of education that you're at right now. Uh, it is entirely optional to fill this out, but we would appreciate it. It helps us get a clear picture of the types of students that are interested in quantum, and then helps us inform DOE about how we can target those programs in the future. Any question about survey? Yeah. Oh, the final exam. Yes. Okay. So in the end, we didn't get together the final exam. So I know. You are the type of students that would be disappointed by this. Okay. And I admire that about you. Okay. I really do. Instead, what we found was we had a collection of problem sets that specific instructors provided. So we have created like a zip file of this. We're going to post that online for you. We'll send out information about it as well. So I know that's a disappointing fact. So we don't have this, cumulative final exam. I'll be honest. That was really difficult when we looked at the lectures and asked, okay, how do we actually write an exam, write questions that covers all of this material that's fair? Because everybody here has a slightly different background and attended slightly different elective classes. So in hindsight, we can do a little bit better on that. Feel free to add that to the survey. But we hope you won't be too disappointed with the problem sets. Yeah.
Is there a way that like official class notes and slides will be distributed?
So there is a website, the qscience.org website. We are posting all of the material that we have onto that website. So if you go to the drop-down agenda and you click on the red hyperlinks, that'll take you to pages that have PDFs and zip files. That is all the information we have. Yeah, and we do plan to maintain that site. So. Typo? I don't have any prizes, guys. So lunch, I mean, yeah, that's a weird prize. Yeah, there you go. I don't know what's in those boxes. Could be anything. So, but I think when we originally were thinking about it, Taman, we were imagining some sort of competition with the exam. But again, that kind of fell apart. So, other questions? And that's right. Independent problem set. Actually, not independent. The problem sets, again, it's a little sporadic. The ones that we were able to collect are intended to be almost group exercises. So we'll have those posted later today. Can work on those this evening. That's right. Yeah. I mean, I take that back. You are welcome to submit it if you're asking questions. You know, was this the right answer? These types of things. We can put you in touch with the instructors. Yeah. Okay. Everybody got the survey link? I need to stop sharing real quick. Okay. Okay, so now we will move on to our morning presentation. Okay, so this morning, for our second to last keynote presentation, we have Professor Kasia Krzyzanowska from Los Alamos National Laboratory. Kasia works in the Quantum Science Center through Los Alamos. She actually leads one of our projects on neutral atoms. She'll be talking today about from Bose-Einstein condensates to single atom arrays. It's Kasia.
Good morning. I hope you can hear me well, right? Okay. I'm really happy to be here, and I hope that I can give you a very good overview of Cold Atom platform. So maybe I will ask you throughout the talk to be engaged. I will ask a couple of questions. Once in a while, I would like to maybe for you answer for me whether you are feeling comfortable with certain concepts, whether you've seen it before. I will ask you to vote. Just would like to understand how many of you seen certain things or not. And my first question for today is going to be whether you like the topic or not, or like the title. It took me a considerable number of times to figure it out, and essentially it was ChatGPT that helped me with that. So my first question is, so I prompt, this is the content, this is what I want to talk about, give me 10 suggestions, and that was my pick. Do you like this pick? Who would say that it's a good one? Just hands up. All right, thank you very much. I think ChatGPT did pretty well today. Okay. So the objectives today is I would like to cover a broad range of topics from cold atoms, and it's because you are a broad audience. So for everyone who is non-AMO, atomic molecular optical scientist over here, my goal is to establish some basic concepts so that in the future, you know what's going on, you can follow more specialized talk on the topic, maybe don't feel so lost when you hear all of the terms of magneto-optical traps and magnetic traps, and then the gates, 2-qubit gates, single qubit gates, atom arrays of atoms, and so on. So maybe if my first question is, who is an AMO in this audience? Okay, we have a few. Well, so for everyone who is planning on using cold atoms platforms in the future on the cloud, because there are such possibilities, there are platforms with single atoms. There is now available platform with Bose-Einstein condensate. So my goal is to explain the underlying physics in such a way that you will be able to navigate those platforms better, understand the underlying physics, and design experiments in more informed way. And for all of the AMO physicists that just raised their hand a few minutes ago, I hope I provide some more in-depth content so that you find something new today. And again, you will let me know whether I did a good job at the end. So the first one will be intro and overview, some basic trapping techniques. I'm not going to go much in depth on many of them. If it was a lecture 30 years ago, talking about magneto-optical traps and magnetic traps would be the key of this topic, but nowadays we are focusing on the next level, so the applications, the computing, the sensing, and so on. And then I will give you some details about single atom arrays and BECs in adjustable potentials. And at the end, I have a demonstration. I will show you there is a service on the cloud that can provide you BC. You can use Python to operate it. It's a real machine, it's a real experiment. I will log into it, I will show you how to use it, and you all are going to be given access at some point to use it. Okay, so why are we talking about cold atoms? What's so good about cold atoms? So first of all, it's the broad range of possible applications. Cold atoms are one of the platforms which is suggested, which is being developed for quantum computing. And there have been quite a few remarkable breakthroughs quite recently. There are also many companies, there is lots of funding, both from like the scientific point of view, but also industry that invests into quantum computing. So yeah, the basic idea is that we use quantum mechanics to process information, enable potentially exponential speedups for some types of calculations. And the state of the art is that there were actually companies showing over 1,000 atoms in single arrays and up to 48 logical qubits. The reason for the logical qubits to be much lower is because we are still at the stage that we need many single atoms in order to encode 1 qubit, almost fault tolerant, because they do tend to be more fragile than, let's say, registers in the computer. There are some surface codes which are for the error correction, has been already demonstrated to a degree, but it's not a full error correction cycle yet. However, the last year was already quite a big breakthrough. Then we have quantum simulation. The idea of quantum simulation is to use quantum system to mimic and study complex quantum phenomenal materials that are challenging to simulate otherwise using classical computers. And now one of the ways you could achieve it is if you had a perfect fault-tolerant quantum computer, you could take your Hamiltonian and do the trotterization procedure so that you just get the full dynamics of the system and you can simulate it on the computer. But there's another possibility that you can kind of map a Hamiltonian that you're interested in onto a Hamiltonian that a system like that, let's say, which is cold atoms and an array with interactions can mimic and show a few things. For instance, a dynamics of quantum spin liquid, Kitaev spin liquid. So there are a few notable demonstrations of this sort of within last year, few years. So yeah, the main question over here is always when would quantum simulate and perform quantum computer, even if we had completely fault-tolerant quantum computer? And the final application for cold atoms is quantum sensing. So measuring change of external parameter exploiting quantum properties of a physical system. And here the most notable example are atom interferometers, magnetometers, and so on. They are not really quantum 2.0, they're quantum 1.0, and here the distinction is that quantum 1.0 refers to using the phenomena such as superposition to gain some advantage. 2.0 would mean that you have some sort of entanglement. And the main reason why quantum sensing is still at the stage of 1.0 is because in applications for sensing, we really care about sensitivity. And we are still at the stage where just adding more atoms is more beneficial to us than trying to create entanglement, which is just more fragile, and we'll have to reduce number of atoms. So in the future, when we hit the limit of not being able to add many more atoms, we will need to move to 2.0 and start using entanglement in, for instance, atom interferometers and sensing to get better precision. So that's an overview. And here's the general idea. Harnessing internal electronic structure of an atom for quantum technology. So basically, we use it for everything. We use it for cooling, for trapping, for encoding information, for detection of the atoms. And here to the left, I have a picture showing such electronic structure of rubidium-87. And my question is this something that you're familiar with? Like, how many of you have seen something like this and feels very comfortable with it? Hands up. Okay. How many of you like seen it, but you would need some kind of walkthrough to understand? Because I'm going to use those a lot. Okay. So how many would need? Okay. So, and who has never seen it, just out of curiosity? What's your background, may I ask? Is computer science. Okay. So yeah, so let me explain you. This is the energy structure of a particular atom. This is for rubidium-87, and every atom is going to have slightly different structure based on how many, what's the nuclei, how many electrons they have, and so on, and the interactions between all of those. So we start from the bottom. Bottom is the lowest energy level. This is where the atom is in its ground state. So, and the ground state is something that's stable. If you put atom in ground state, it's going to stay there for a long time. So, for instance, for rubidium, this one here to the left, this 5s1/2, this is our ground state. 5, the first number tells you what's the principal quantum number. So what's the electronic shell, how far the atom is, the final atom, not atom, how far the electron is from the core. And then S tells you what kind of orbital it is, whether it's the orbital which is fully symmetric, whether this is the one that looks like the dipole moment or the clover shape. So, S, P, and then D and E and so on, they tell you which kind of orbital it is. So you can see here you have S, and then you have P and P. So there are different options. And then another thing that we have is that there is interactions between electrons and the nuclei that electron and its spin and the orbit, which creates certain energy levels to split further. So here, for instance, we have the splitting. And then each of those, depending again on the atom, but for rubidium is going to have magnetic sublevels, meaning that they can be completely neutral. So if you put it in a magnetic field, let's say if atom is the state 0, they wouldn't interact with the field, but if the other case, they would be, for instance, attracted to some field. And then we use this electronic structure to control the atoms because we can shine laser light, which has a frequency that, for instance, couples this state with this state. And what we can look at is the interaction Hamiltonian between this entire complicated electronic structure and our laser, which, for instance, has a laser frequency omega L. And this Hamiltonian, the evolution of what's going to happen with the atom is going to depend on the Rabi frequency, which is kind of a natural oscillation for the given atom between those energy levels. So just to summarize, we have different energy levels. So this is the lowest, a bit higher, 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 higher. This is not up to scale. Those energy levels, for instance, this one is much further. It's a ground state. These are much higher. Okay, the question. I couldn't hear you, excuse me. Oh, okay. So we do have a split here between this level and this level. This is the actual split that you can see in an energy spectrum. And then when it comes to magnetic sublevels, if you don't have any external field, it's going to be degenerate. You can put in an external field and then you will see the shifts. And then you live the degeneracy. Okay. So yeah, I will be using rubidium a lot as an example. So the question is why? It's because the electronic structure is pretty convenient for encoding quantum information and for manipulation for cold atoms with cold atoms techniques. And also rubidium is very popular because of technological reasons. It's convenient. It has convenient sources of atoms, basically just pieces of metal that you heat up into vacuum chamber. It also has very convenient wavelengths to manipulate, which is 780 nanometers, very easy to obtain with semiconductor technology. Any question at this stage? Yes? Okay, the question was whether rubidium is stable. You're talking stable in the sense that it decays isotopically, for instance? Yes, it has 1 free electron. Okay, yeah, this is why I'm trying to, cover all of those so that we all are on the same page. So yeah, rubidium has a 1 electron, valence electron, which can be typically ground state occupies over here. So this is that lowest shell. If you were to expose it to a laser light and then excite it to one of those states, then it's not stable. Over here, it's going to decay down to the lowest ground state. So now actually the truest ground state, lowest state is obviously this one on the bottom, but the splitting between those two is so small that even if you put this one here, if electron at this one, is going to stay there for a very long time. It's just because the difference between those two energy levels is 6.8 gigahertz, which means that any kind of decay would take, well, substantially long. I actually don't have a number off the top of my head, but we just call both of them stable ground states for that reason. Uh-huh. Well, if electron would go somewhere else, then we are talking about ions, right? And this is not then a consideration for neutral cold atoms anymore. So neutral cold atoms always make sure that that electron is still here somewhere on those shells. Even if we are exciting it to Rydberg states to have some interactions with other atoms, we always make sure it's here, it never goes to continuum. Yeah.
Chemistry classes, like those where you go, is that it was like S and P, but the problem is that I don't understand the 0, 1, 2. There's 0, 1, 2 here.
Oh yeah, so magnetic sublevels. Oh yeah, over here.
Why it's half, not S 1, S 2.
So that relates to the total. Oh, you're asking hard questions. I would have to. I was looking through, trying to remind myself all of the numbers. That relates, I think, to the total spin. Yes. Someone who can correct me in this case. Is it a total spin? Yeah. It relates to the total spin of the atom.
I have another question.
Okay.
If it's some specific energy to go from S1 or S to the P, right?
From here to here, for instance, D1 or D2. Yeah.
Half the energy. Like if energy X to go from one level to the other. So what if I gave it half this energy or a fraction of the energy?
Okay, so here we are getting into, I think, small nitty-gritty parts about the picture of the interaction with the light. If it was a photon with just half of energy, it wouldn't go anywhere, right? Because it wouldn't be the right one to absorb. But the point is that we have a laser light that has many photons with a given frequency that can couple those states. So what you do, you have a laser pulse that has certain duration, and it can drive your transition, not sometimes fully, you can kind of leave it halfway through, which creates a superposition of those two states. So I don't think I would say it is that you just give it half energy, but you just had a pulse which had an exact duration to run it between halfway through between those two levels. But if you had a photon that didn't have the right frequency, so basically was half the, half the frequency of what we need, it just wouldn't excite you to that stage. Well, it's also partially because the kind of interaction we are looking at over here. So we are considering, if you look here at its semi-classical picture. So we have quantum atom and classical light description. Shall I move on or more questions here? Because we need, okay.
What is the R significance of the R dependency?
Of R dependency here. Yeah, so it's well, it oscillates with time, so all of the atoms, regardless where you're standing, is going to see the full, planar wave eventually. It's not here. This is not about using standing wave in this case. No.
Position is we're positioned in space.
Well, yes. I mean, this is. Well, yeah. It's a position in the sense that you have the wave that is oscillating, but like at each point of time, it's going to oscillate through its whole period, right? I don't think it's really very important part of this Hamiltonian, but you could also select particular point in space. I think I'm going to move on because we have plenty to talk about. Okay, well, so that's what we are going to talk about today. I'm going to tell you a little bit about magneto-optical traps, because when we start with cooling atoms, with trapping atoms, they're pretty hot, they move very fast. And it's not that they are not quantum intrinsically, because they are quantum intrinsically, but we wouldn't be able to measure them or to manipulate them if they were to pass through our vacuum chamber and split of a second and just crash in the wall. So magneto-optical traps give us cooling temperature, so the velocity of the atoms, right, it gets lower, of about 140 microkelvin or maybe 15 microkelvin, depending on how well you adjust the technique. Then from there, we can either trap atoms further magnetically, and they do need a magnetic state which is trappable, so attracted to a certain place in the potential. We also have dipole traps. So this is when you have a laser light. So basically, laser light interacts with the atom and induces the dipole moment. And that works for all polarizable particles, not only just atoms, that can be even bigger particles. You know, there are demonstrations where there were kind of biological samples moved with dipole traps. And this works for all magnetic sublevels, which is great. And then further from those two, there are the basics that pretty much everyone has to use in some kind of combination. We can go further. We can do either evaporative cooling to get bosons and condensates of dilute gases. We can provide evaporative cooling and some sort of way to create arbitrary patterns to get interesting shapes of those BECs. We can also take the dipole trap and then get the standing wave. And this way we can get optical lattices if we have it in few directions overlap with each other. Or we can use collisional blockade and arbitrary pattern to get single atom arrays, which we know is pretty useful for computing. Okay, so starting with magneto-optical trap. As I said, the first few slides are going to be mostly an overview. I'm not going to go very much in depth, but I wanted you to have some idea what is happening in the lab typically. So magneto-optical trap typically is a necessary first step. And the reason for that is because typical stars of atoms in vacuum chamber provide gas in a room temperature at least, or above, depending how we do it. So when it comes to room temperature, which is, I don't know, 25 Celsius, 70 something Fahrenheit. I'm still learning, you know, after moving to US. They are moving very fast, right? And therefore, we would like to slow them down. What we are going to do, we will use radiation pressure, so a momentum exchange between photons in the beam, in the laser beam, an atom to slow down the atom. So the way it works is depicted here. We start with an atom that is moving in certain direction with certain velocity, and it's exposed to a series of photons moving against it with certain momentum, which is associated to the frequency. Because it's close to the resonance, atom can absorb them. And as it absorbs them, well, the velocity, there is a momentum exchange, so the velocity will decrease. Eventually, the atom has to give away all of this stored energy because it's now stored in excited state, so you have to go back to a ground state. So after it releases this energy, it's going to give a little bit of a momentum kick. But because it's doing in all directions sort of uniformly, there is a net exchange, which will eventually take you from the initial velocity to the slower one. So if we do a little bit of like back of the envelope types of calculations, when we have plenty of unreasonable assumptions, for instance, that every photon is going to be absorbed, and you know, as the atom actually slows down, there is a different dependence of how many photons can be absorbed because they are getting closer or further from resonance. But anyway, if we do discard any of those, what we will see is that it will take us about 1 millisecond and 5 to the power of 4 photons to slow down atoms from the room temperature, which is 300 meters per second, to about 1 meter per second, which would be 10 millikelvin. It's still very hot. We normally can use magneto-optical traps, which you can see here. This is the given configuration, where you have an atom and 3 of those beams working on this atom from different directions. It's basically a pair. So there is a pair of a beam going one direction, another direction, and so on. So it's a configuration of 3 pairs of counterpropagating beams close to resonance and magnetic field gradient. So this is magneto-optical trap configuration that allows us to have sort of state position-dependent scattering of those photons. So if an atom is further away, it's always going to be pushed to the middle, to the center. Allows us to cool to temperatures of, with just Doppler cooling 140 microkelvin. This is what the theory would predict for the state-dependent, position-dependent scattering. And there is another phenomenon that lets us go even lower if we are really careful with the adjustment of the trap, 15 microkelvins and so on. I think I personally stopped working last time and trying to make it better about 20 microkelvins in my lab because good enough. And we have other things to do, move forward, right? So here, this is what it would look like, you know. Here I'm showing a picture of strontium lattice optical clock, which shows the cloud of atoms glowing inside of the vacuum chamber. The reason why it shows this time strontium instead of rubidium is because rubidium would scatter at photons with wavelength 780 nanometers, which humans cannot really see. But when it comes to strontium, it's much nicer transition. It's closer to blue. So what we can see is with a naked eye, you go to the lab and you see when the MOT magneto-optical trap is turned on, this beautiful bluish glow of atoms just sitting there in the chamber. So any questions over here? That was a very high level, just wanted to say. Okay. So the next one, let's move to magnetic trap. Once we have atoms already slowed down, cooled to certain temperatures, we need to somehow store them more conveniently, perhaps cool it further or just manipulate it in space, give it different shapes. So magnetic trap is one of the ways to do it. So I told you, remember there was a ground state that was split into hyperfine structure, this one, the bottom one and the top one, and there were magnetic sublevels over here. If you expose it to magnetic field, so external field, all of those energy levels will shift a little bit. And generally speaking, you can always see this sort of energy shift or any energy shift in the atom as a potential, effective potential, which then can be a trapping potential. There is a force that comes with this potential. So yeah, you live the degeneracy of those levels. You create an energy shift. This is a potential, and therefore you're just trapping atoms magnetically by Zeeman interactions. This is the Zeeman interaction of the electron spin with inhomogeneous magnetic field. This requires non-zero magnetic moment. So actually, not every atom can be trapped this way. Vast majority of alkali atoms and so on, yes, they have configuration that allows to do it. There are so many geometries because effectively this problem of trapping atoms with magnetic trap just boils down to can we create such a magnetic field that has a gradient and minimum somewhere? That's all what we really need in order to atoms to be attracted. So there is a quadruple trap, for instance, two opposed coils with different opposed currents, which creates this kind of like U-shaped traps. However, the most impressive and standard technology nowadays is magnetic traps on chips, which is a really mature technology. So here's a picture of this a chip that would trap atoms magnetically just above the surface of this chip. And the reason it works is because if you have just a wire, imagine you have a wire on a substrate, and there is a current going through it, you're going to have associated magnetic field that goes around it circularly like this. And then all you need to do is to give an external magnetic field bias, and there is going to be a minimum somewhere just above the chip where the atoms can be attracted. And this is at least in one direction, and if you want to, so it would be infinite guide if you just had it forever. If you want to just cut it off at some point, you bend the wire. This is the way to do it. That's why you can see, chips have those kind of like bendy structure. there's a lot going on chips. Honestly, I've never myself worked with chips, so I'm not really sure exactly what are all of the other electrodes for, but um, I know it's mostly for magneto-optical traps and similar things. Any question with this one? Yes, please. Oh, large trapping volume. Well, this is subjective. I said actually that it has large trapping volume. It's a nice thing. It's in comparison to dipole trapping typically. So I'm going to talk about dipole traps in a second. Yeah, so the reason why magnetic chips have better trapping volume than dipole traps is because with a reasonable current, you can create sort of reasonably big magnetic field to store them. And it's going to be length of tens of micrometers and so on. So you can create a cigar shape BC in it of this size. If you go to trapping with light, you will see later on you would need a tons of laser light, and it's just difficult to provide that much power in optical way. So I would say that this large trapping volume is in respect to other techniques, mostly. That's how I would define it. Okay. Okay, going back. Now let's focus on dipole trap. So with dipole trapping, what we use is light which is far from resonance. So we are going to have an atom and shine a laser beam, which is typically focused around this atom. And far from resonance means typically 50 nanometers or greater. And this one is going to have slightly different effect that light that would be in resonance. In resonance, you would have photons to be absorbed. You would drive the transition between two different levels. In this case, you don't really drive transition anymore, but what you do, you create an external electric field. You create AC Stark effect. And this effect, again, is simply a shift of the energy levels. And as we know, shift of the energy levels can be seen as a potential, which is effectively a trapping force later on. So yeah, that's what it would look like. We have our, again, rubidium in this case. We start with the ground level. We don't even care about the hyperfine structure in this case. All we care is that it's just somewhere here because it's so far detuned that you are kind of targeting all of the states at the same time. And then you shine this laser that is very far detuned from all of the other transitions. So it's far detuned from those first transitions and from the next one even more, right? So there is going to be a shift that comes with it that shifts the entire, actually all of the levels, but the most important one is the one in the ground state, because this is where you're holding the atom. And this shift, which is a trapping potential, can be expressed in this way, where you have the detunings from the excited states. You can see detuning 1, detuning 2, and also a couple of other parameters such as intensity of the beam that you're using, and also saturation intensity, which is sort of intrinsic feature for every atom of how many photons they can scatter in a certain amount of time. So you can see that this trapping potential, first of all, the stronger beam, the better confinement we get, right? It's the better shift, a bigger energy shift. Another thing you can see is that the tuning is going to matter, how big the shift is, so how strongly we can trap atoms, and that they also can have different signs. So, you could take this state and couple it here, far detuned from those, but you could also do this on the other side. Like it could be just way above the resonance, right? And because you can either tune it above or below, you have two different types of traps. You have red detuned traps and blue detuned traps. So in the red one, atoms will be attracted to the highest place in the potential. So for instance, if you have like a beam which is very focused, atoms are going to be attracted in the middle. Or in the case of blue, they are being repelled by the high potential. So if you want to trap atoms, for instance, you would try to create a hollow beam, and the atoms are going to be like stored, you know, by the walls around it. Any question at that stage? Yes, please. The size of the focal spot is as small as we can make it. I don't think we will be able to go as small of the atom, right? Because it's very small. What we are limited is the diffraction limit of optics. So typically we go as low as possible. So it's going to be below 1 micrometer size, maybe, you know, 2 micrometer size, something like that. So typically we will go diffraction limit, but combined with high enough intensity, you know, if you're having certain amount of intensity and you focus it that small, you really get very big shifts or really strong potential to hold on to atom. So yeah, micrometer, lower than micrometer, depending what wavelength you're using, you know, depending on the wavelength, you have different diffraction limit. Any other questions? Okay. So we went through those. So let's look at the interesting part now. I said the interesting part is because all of those are kind of standard techniques nowadays in cold atoms. So I think it's good to know how it works, where it comes from. I don't think if you're an AMO experimentalist, you definitely need to know it in depth because this is what you deal with every daily basis. You have to optimize it and so on. But for everyone else, even if you want to use some kind of the platforms, it's good to know how it works because it might be a part for like the optimization of the experiment, but you don't really have to know more details in this case. So the interesting part over here is now this. This is the state of the art. This is what the frontiers is happening, where all of the effort recently is put in. And just remember that what I'm showing here also is just a simplified picture. There can be sort of a combination of different techniques. And in fact, very often we'll start with magneto-optical trap and then go to magnetic and then to dipole trap, or you have dipole magnetic with some kind of blue potential to repel. There are many combinations. So let's go further. I'm going to talk about single atom arrays. First, cover trapping techniques, then Rydberg interactions. So it's how you can create tunable interactions between them. I will talk a little bit about analog simulators using those techniques. And how do we create digital quantum computer, which has qubits, gates, and so on, using single atoms. Okay, so moving on to the first trapping techniques. So as we discussed before, there is a cooling with laser light, so it's MOT and other techniques, which will allow our atom, actually there are many atoms, but we are only focusing on one right now, our atom to first slow down enough so that when we turn dipole trapping, the atom actually gets caught in that potential, because the potential is deep enough for the temperature of the atom. So now this atom is not going anywhere, it's just oscillating, bouncing somewhere in that dipole trap potential. And the way we do it, and actually it was related to the other question, is that in this particular case, what we will do, we will use high numerical aperture lens. So if we have a laser light that comes through this lens, it's going to focus very tightly down to the diffraction limit. And it's important that it goes down to the diffraction limit because when it's a very tight trap, we have something called a collisional blockade. So that means that there is a light-assisted collision happening here that enables robust single atom loading. So instead of loading many atoms with some Poissonian statistics, the trap is so tight that if you happen to have two atoms that try to go into this trap, one of them is going to kick out another elastically. So what you are going to see as you turn on all of the lasers and you look at the imaging, and imaging is just photons being scattered by atom in the trap. So you're looking at the camera or photodetector that counts number of photons. What you see is this kind of statistic that you have no atoms and then you have one atom and then you have no atoms and one atom. And it only goes back and forth between 0 and 1. So you are loading single atom or none, and it's given, never more. Which is a very nice feature. I mean, it's not that simple, generally speaking, to prepare states where you only have one of something, like an atom or a photon or so on. So yeah, so we are using Katarzyna blockade to create single photons. So how do we do it? So what do we do next with it? So once we have just the single photon, what we can do, we can create an array of them. How do we create an array of them? There are a few ways to do this. The most popular in this in this field is to use spatial light modulator. The way it works is that you have a laser beam, Gaussian distribution, that comes here and hits that liquid crystal that can be modulated, it's deformed and so on. And the light gets reflected, and we imprint a phase mask onto the light, which this picture is artistically depicted as wiggles. Hope it works. But basically, it's a phase mask that we imprint over on the laser light, on the wavefront. And then when it goes through the lens and it gets focused in the plane of the focus, we get a certain pattern that we are aiming at. For instance, over here, we can create, quite a few focused spots. So this is what it looks like if you were to do this in the lab. This is the phase that you imprint on spatial light modulator. And if you were to measure the beam somewhere before it's being focused, it would look kind of messy, doesn't have any pattern. But then as it goes through the lens and in the focal plane, you can actually resolve this very nice pattern. It's because it's all kind of represented in the Fourier space, right? Then if you know that this is where the light spots are, now you're like, okay, it's very tight. All I can do is to load 1 or 0 atom in each of them. So you turn this on when you have a cloud of atoms just bouncing around. And what you will see is some kind of a picture that, maybe not doesn't look the best at the first glance, at the first time of loading. But if you average many times, you do see that you start loading atoms into arrays on average. So on average, you see there were some holes over here, but on average, you get the loading in each of them. So you kind of reflect this pattern with loading of the atoms. And now, you can change the phase, you can change the geometries in the same way, make some loading. So these are kind of early experiments. Early, a few years ago, but 2019 is already the past decade, right? Of my colleague, where they were loading atoms. And the main thing over here is that, well, for quantum computing purposes, or basically any kind of purpose, especially simulation, you would like to have a lattice which is regular, right? You don't want to have too many holes because it's not very usable. So in order to get a pattern like this, what you do, in fact, you just rearrange the atoms. Those spatial light modulators are very flexible. You can change this phase continuously and sort of like, have this beam here and kind of move it around. And if you do this in a smart way, atom is going to be there, will not fall out, and is not going to get excited either. So there is a certain trajectory you can move it around. So let's say you start initially with, not completely filled array, so you have atoms in few places. Then what you can do, you can exactly shuffle them by moving those optical tweezers. And in the final stage, you do have very regular lattice, although obviously you started with, let's say, bigger lattice, but with holes, and you end up with smaller lattice, but uniformly filled. So for instance, we start with 8 by 8, and this is sparse, good enough to get filled with 6 by 6. It takes time though, it's going to take time about 100 milliseconds. The reason for that is because, as I said, you first of all want to avoid moving it too fast and colliding with other atoms so that you would lose it. Another thing is also you kind of have to be smart how you rearrange it in a sequential way. So there are actually algorithms to figure out how to do it most optimally, optimize the trajectories, parallelize and stuff like that. This is now becoming standard technology. It was 2016, right? But then since then, there were quite a few impressive results. Like, you start with every of these feelings and you get anything, including a Valentine's Day version of your atom trap with a little sweetheart. This is a group from Eiffel Tower, from France. I bet they have a poster, out of, of this Eiffel Tower somewhere at the Eiffel Tower. I mean, I'm sure that like in the restaurant at the top, there is a picture of it. There should be. That would be a good marketing, right? So it is a good marketing too, because what they did is, this is a two-dimensional option of it, but they managed to have a set of beams in such a way that they created three-dimensional pattern. And out of this three-dimensional pattern, they created the Eiffel Tower with 126 loaded single atoms. It's a very impressive, it's beautiful work. Also a little bit, I would say, show off, right? That's okay. We can forgive scientists a little bit of show off. We will move to Rydberg interactions now. Okay, questions? Mm-hmm. Yeah. Yeah, it's extremely hard to do it. So the thing is, when we look back how it's made, right? Let's see. Over here. When you have only 2D, it's kind of a simple system, right? You bring it here and it's a very easy mapping. There is pretty quick algorithm efficiently mapping it from here to here. If you want to create a three-dimensional, yeah, it's just hard. You need more optics to add over here, more complicated phase imprints and so on. And the problem is that you don't actually really have much space, because when you look at these lenses, they are high numerical aperture lenses. They have a working distance of like 1 centimeter. So you need to put your optics right against the vacuum chamber, like the cell. Then you have a window for the cell. Then you have just like few millimeters from the window of the cell where the atoms are actually spatially held, and your lens is literally already against the cell. And then you also have all of the other optics that is there for magnetoptical trapping, for dipole trapping, and so on and so on. So yeah, it's kind of not surprising that they did not move with it. It's just because also it's not very necessary for simulation or computing purposes at this moment. I think, yeah, that's a good point. There might be some work towards it. I'm not very familiar. Where is it at? Do you know where is it at in terms of meta lenses? No, they definitely wasn't. No, like even nowadays, typically what people will go with this high numerical aperture lenses is kind of standard objectives you can buy. It's because the nice thing, okay, one thing that you would like to do is to make sure that this entire area is kind of very well addressed, that the field of view is very flat for the lens. So it's just not a trivial problem to have a set of lenses in such a way that you have high numerical aperture, but also very flat field of view, so that you can grow and grow and grow the array. Because eventually what is the idea is you would like to have not just couple by couple, but you would like to have 100 by 100. And that moves your field of view by hundreds of micrometers. And this is the direction towards which the research is going towards today. Okay, I am much behind the time, so let's see, let's try to speed it up. Okay, so we loaded our array. It's impressive, many atoms. What do we do with it now? So the thing is, when the atoms are in the ground state, they don't really interact strongly, right? I mean, they don't. Because they only interact via van der Waals interactions, so it's weak. However, what you could do if you wanted them to start interacting with each other, well, you can couple them to Rydberg states. So Rydberg states are these highly excited states where, let's say, the valence electron is really the high principal quantum number orbital, somewhere far. Those atoms also tend to be kind of physically big, right? It's really big. And in this case, you will get stronger interactions. So this is how it works. So here's the column expansion for the system of those two atoms. Let's say you have two atoms, each of them has one valence electron, and you would like to see the Hamiltonian between them. So it's going to depend on the distance between them relatively, as well as their dipole moments, right? So effectively, if you look at the terms, the main term is going to be this term and this Hamiltonian when you have the dipole moments of each of the atoms and the distance between them. So if we use second order perturbation theory, you can see what would be the strength of such an interaction. You will also see that if we are going to go into higher principal quantum numbers, this is going to be pretty strong. But you need to bring them close because the interaction disappears as 1 over distance to the power of 6, right? So you can imagine if you start with atoms 1 micrometer apart from each other or atoms 10 micrometers apart from each other, that's a very different scale of the energy shifts. Well, how do we use it in quantum technologies? Well, we are using it because it has a nice feature of creating something known as Rydberg blockade. So the way it works is that if you have two atoms, right, and then you shine a laser beam with a certain coupling frequency, which wants to excite each of these atoms to the Rydberg state, if the Rydberg atoms are far apart from each other, they can each absorb the light and get into Rydberg state is okay. So if you look at the energy structure of both of these atoms described at the same time, just kind of standard thing to do over here, you will see that there is energy for both of them being in ground state, an energy level for one of them being in ground, one in Rydberg, and vice versa. There is a superposition of those. And then both of them being in Rydberg state. If they are far apart, this is the structure. You can excite all of the possibilities. However, if we start bringing one of the atoms closer, at some point, the interaction I just showed you before that was scaling like 1 over distance to the power of 6, you will see that this energy levels is becoming shifted. It shifts due to that formula I showed you on the previous slide. So now the problem is that, well, but while this one doesn't really shift, because here only one is in Rydberg state. So what you will see is that you can only excite a situation where one of them is in the Rydberg state, but you cannot excite two of them because the energy shift makes this laser light of resonance. So you just don't get them. And this is what we call Rydberg blockade. Rydberg blockade means that you only have in a certain radius one Rydberg atom. And it was showed first in cloud of atoms where they just shine the laser light and they could see, okay, so the Rydberg atoms are at a certain distribution and not closer to each other. And now they also use it further for gates. So as I am rushing through some of the topics, are there any questions here? Okay. Let's move further. Atom analog simulators. So when we have those techniques, now the question is, what can we do with it? What we can do with it is we can take the fact that we have interactions in the Rydberg state, And we can take a laser that's going to drive us from the ground state to the Rydberg state and back all over again. And the Hamiltonian of such system is going to look this way, where we are going to have a ground state and a Rydberg state and many of those atoms. I stands here for the atoms, so you have to account for all of those possibilities. And what you're going to see is that there is going to be the energy shift that comes obviously from being in the Rydberg state and the interaction that comes between different neighboring atoms in Rydberg state being up or down. So the thing is that this kind of Hamiltonian can be directly mapped onto a dimer model, right? Where you have the spins up and down, which are interacting like in a chain. And this work has been shown quite recently. So what further you could do, once you have these dimer interactions, right? You could arrange the atoms on the lattice in such a way and such a distances, then you could create a Hamiltonian of something that is interesting to you. For instance, quantum spin liquid. And there is a lot of going on this picture. This is actually directly from the paper, so I really suggest for everyone who is interested to go there and read it. But the idea is that atoms were organized in this Kagome lattice, right? And then what we can see is that we are coupling them to the Rydberg states. They start interacting at dipole, so the dipole dimer model, like in a material, you would see, the spins on the lattice just interacting with each other. So like you have one up, the other down, and they just kind of, flip each other all the time. So what you can see is if you have lattice like this, you could create a pairing between those. So those things are the pairings between different interacting atoms. And then you can create, you can add energy to the system by distorting it, for instance, or exciting or removing. And what you will get is you will get all of the combinations of all of those possible pairings in between each other. And this is directly what, is interesting in quantum spin liquid. If we want to study a dynamics of system like that in materials, but we are using cold atoms to emulate it. And I would probably suggest for more details to look deeper into those papers. Let's see. Okay, I'm going to move then to the next stage, but are there any questions so far? Okay. Pardon? Yes, it's the Rydberg dipole. Yes, but yeah, you're right. I'm sorry. I said spin. What I meant basically was this dipole interaction up and down. It's just whenever I think about up and down, I would say. But you're right. It's a dipole. Any questions here? Okay. So let's move to single atom arrays for digital quantum computing and how it works. When it comes to quantum computing, we have a couple of criteria that we would like to satisfy in order to have a universal computer, right? So we want scalability, and actually we're getting closer there, over 1,000 atoms. The problem is they're not logical qubits yet because we would need to group them into it. But yeah, we can load many atoms. There needs to be a robust initialization process. We want long coherence times, which we actually are going to get in our ground states, universal set of gates, and then the measurement. Let's see how do we do it with atoms. So we can store information in different ways. If we take, let's say, alkali atom, and we have one valence electrons, and we have this hyperfine splitting of the ground state, we can encode information in the ground state between, the f equal 1, f equal 2. It's going to be 0 or 1 in any way we decide. So this is one way of doing it. However, there are other options where we don't necessarily have the splitting, unfortunately, but we have something which is called a metastable state, which is stable for long enough for us to encode the information for the duration of the computation. So these are other options to use for storing information. We'll be focusing mostly on that. It's probably because many of the companies focus on this particular application. So how do we initialize it? Again, there are many different schemes. One of the options, for instance, is that you start with the atom in both populations, F2 and F1, because you don't know, it's always a mixture. And you expose it to the laser light, which couples it to, let's say, from 1 to 2. So you are now pumping the state from the bottom to this state. And the thing is about the state that this can decay back to the ground state, but it can only, so it can decay to the state F2 or F1. So if we keep pumping it for long enough, what we are going to do is that eventually there's going to be no population on the bottom. There will be everything in F equal 2. In addition, if we want to make sure that it's in one specific magnetic sublevel, we just need to use circularly polarized light to kind of to use the principles of the decay. It cannot decay from 2 to 0, and so it needs to decay 1 apart. So we can pump it to the specific state. There is another option which is more complicated. So if we look closely at those states, at those levels, right, we can also again pump everything from F equal 1 to 2, but now we can expose it to the magnetic field, lift the degeneracy again, and all of the atoms from here are going to decay back to the ground state. But there is something called electromagnetically induced transparency, meaning that for this particular state at MF equals 0, this laser is going to be on resonance with this laser. And it creates such a called dark state, meaning that this one just cannot be populated. There is a way to work out the Hamiltonian for it, but this is a convenient thing because then you pump up everything from F equal 1, and then you end up with MF equals 0, which is nice because it just to the first order doesn't interact with the external fields, and in the lab there are always some residual external fields. Okay, single qubit gates. How do we do it? So with single qubit gates, there are two options. Again, you can use microwaves and just directly drive transition between two of them. So you can just use an RF antenna, which is going to be just a piece of wire, right? And then a very nice stable RF signal generator. Or you can use Raman transition. So you have your atom in certain state, and then you go through the excited state and back. So you're using two photon coherent transition. You make sure that both of them are driving it coherently. So this state never gets populated because it's detuned. So you end up from here, and this is typically really preferable method. It's just because you can address atoms individually this way. Whereas here, when you have antenna, you sort of kind of blast all of the atoms at the same time. And finally, two qubit gates. Again, there are quite a few different schemes. Early stages of quantum computing with cold atoms started with fast pulse initialization. And there were some demonstrations of entanglement in arrays and so on. This scheme is not the leading scheme. There were some technical issues with that. Now, the leading scheme is known as geometric over here. And this one has a fidelity record of 99.5%, and it's really the one that everyone is focusing on. However, just to let you know, all of those gates are based on Rydberg blockade, and every single of them you're going to see that there is this transition through Rydberg where they kind of shift the energy levels. Just wondering how I am with time, you know. So maybe without getting into details, I'm going just to quickly show the evolution. But the idea is that you have two atoms close to each other, right? Again, if you try to excite one of them to Rydberg state, it's going to be interacting with the other one. So we have a couple of options, you know, we can have start with atoms in 0 and 1, 1 and 0, and then try to get it to this combination of states. So one of them in Rydberg, or you can try to start with 1, 1 and a combination of them. And essentially, yeah, what you have is a different trajectory. So if you start in one type of state, you have a trajectory that goes back to the same state with certain phase change. But if you start with the other state with this particular scheme where you start with one pulse and another, you just get another phase. And this phase is what's going to tell us it's a phase gate. I'm sorry, I'm really rushing through it at this stage, but I wanted to get to the point later on that is kind of important for me. So 10 minutes? Okay. Yeah. No, that's okay. 10 minutes. I'm going to finish. I'm just probably, you know, if you're interested in how those gates actually work, because it's a little bit more complicated, maybe I'm going to leave it. But basically, this is control phase gate. So we have different phases, and you can see that one is twice the phase of the other. That's all we need to know. And you can devise a set of universal gates from that following. So yeah, state of the art is that maybe not everything has been achieved so far, but there have been a really impressive demonstration of the arrays with single atoms where they would cluster them into logical qubits. They had also ancilla qubits for computations. So they showed a couple of surface codes. It's really impressive. So yeah, if you want to play with that, that's possible. Okay, let's move to the next side of the topic. So BECs in adjustable potentials. Yeah. Pardon? They perform, yeah, it's fidelity. They perform better. And I think, I really don't remember exactly what was the main problem with the fast gates. But yeah, the problem was that, yeah, we couldn't get high fidelities with those. And it seems that it was a problem with, yeah, maybe stability of perhaps how stable some sources had to be. I'm not really sure exactly in this case. Which one? Oh, I mean, Mormon Sound, I think it's still in the development, right? Sorry. So I think this gate is actually still under development. It might be good. It's kind of a dressed approach to those gates, right? But I'm sorry, I don't think I don't have answer on top of my head why this became the leading technology. There were some significant issues with the fast pulses. Although this is kind of easier to understand though, if you actually delve into the scheme. It's a very simple scheme. This one is more difficult to understand. And it's also just the phase, where here you could have, full rotation if you wanted. You could go from one level to another. It didn't have to be only phase. Yeah, I'm sorry, unfortunately. Yes? Yeah. Okay, so we are getting out of my realm of expertise. Is it possible to decompose swap gates in terms of some other universal gates, like control knots and phases and rotations? Then this is how you would do. You would take the swap and then just decompose in many gates. It increases depth of the circuit, but in atoms, I don't think I know of any native gates in atoms that could be a swap gate directly. Well, I think, okay, so the question is there a swap gate, a native swap gate in cold atoms? I don't think there is. I'm not sure whether it's actually possible. You would typically decompose them, but someone would correct me if I'm wrong. Okay. Okay, let's go to BECs. So BECs, Bose-Einstein condensation, it can be observed in many different systems because it's just a general phenomenon that occurs everywhere. I mean, not everywhere. We need the bosonic particles, right? And we also need, we can observe it only if we have a temperature below a critical temperature, which will be different for each system. So there are examples of different Bose-Einstein condensates. So for instance, some of the phenomena in superconducting metals can be explained as a condensation of pairs of electrons. Similarly, in high temperature superconductors, you also can explain some phenomena as condensation of pair of holes. So here in this case, each electron is not a boson, it's a fermion, but a pair of fermions is a boson. So then you can have a condensation of a particle like that. And many more, there is Bose-Einstein condensation atomic nuclei, but this is not something very, like you can see it in a spectrum, it's not very interesting because there are not that many particles in nuclei and so on. However, the important part is that properties of all of those systems are quantitatively very different, even though all of them could show potentially Bose-Einstein condensation. But why are we actually studying it? What's interesting about it? It's, well, most of all because we can. So Bose-Einstein condensation was predicted, I think 1924 was actually where the first idea came out from Bose and then 25. But the first realization of it came with in dilute atoms, in this particular case when we have rubidium, in 1995, right? So it's been a long time, and ever since we just have a chance to study it. And what's interesting is that in the BEC and dilute gases, we can observe quantum effects on macroscopic scale. It's not that those quantum effects such as superfluidity exist because of BEC, but it's because of BEC that we can observe them better. For instance, we can create vortices and we can see that there is movement of those vortices without viscosity in the BEC. Nice thing is that we have a variety of models to describe those systems very accurately. So we have Gross-Pitarsky equations and so on. So we can model them macroscopically, sort of. It's one-wave functions that we model that just follows Schrödinger equations, and then we can compare it with the results from the lab. And there is application of Bose-Einstein condensates in quantum sensing, for instance, atom interferometry. And there's the entire field which is focusing on trying to move atoms around in the arbitrary potentials. And also we can use as many-body simulator. Many-body treatment is just very complicated. So if we have something where we can create a system like that, which is going to be useful. Okay, that is, okay, who has had a Bose-Einstein statistics in their physics class? That's something that I expect many of you will Okay. Where does it come from? So Bose-Einstein statistics come from the fact that bosons are indistinguishable. So the statistics of occupation of different energy levels and the fact that bosons can occupy each of them makes it different, for instance, from Maxwell-Boltzmann distribution where particles are distinguishable. So if you, the best example would be if you have two coins, right? And you want to flip and ask what's the probability that you get two heads, for instance. In the classical world is going to be 1/4, right? Because these coins are distinguishable. However, they will behave like a boson, like bosonic particles. Then this indistinguishable means that it doesn't matter which one flipped, up or down. So we get rid of one of the options. They're just the same. And therefore, you have 1/3 probability to get both heads up. And this is what happens with the statistics with bosons. If you have different energy levels and you want to see how many different configurations you have that bosons can occupy them, and because they're indistinguishable, you can kind of create all of these possible configurations. This is one level, another level, and so on, and group them together. Derive from it the statistics. I didn't put the a formula here explicitly. I just didn't think it made sense. It was a little bit complicated and kind of integral based. So basically, but what you see is that if you look at the statistics at this of the occupation for the bosons in terms of the energy, of the system, which is big T, and then you will look at the occupation for each of the energy in that system, you would see that if we are above something known as critical temperature, it kind of looks like Maxwell-Boltzmann distribution, which sort of makes sense. But then as we are decreasing and decreasing temperature, it becomes sharper and sharper to the point it becomes really sharp around the zero. And then what turns out is, well, this formula didn't take into account the completely ground state. But as you are decreasing, in a mathematical sense, you will see that there are atoms that start missing from that distribution. And they are missing because they're all going to the ground state. So you start with distribution of over all energies, and eventually all of them, as you're decreasing the temperature and you pass a critical temperature, all of them go to the ground state. And this is what it looks like in the experiment. You will start with atoms in the potential, which is like a ball, right? So they are kind of spread over all possible places. So it looks like a big spread Gaussian. And as you're decreasing the temperature, they are all finally going to sit in the lowest energy level, which is just at the bottom of the ball. So that's how we explain the peak from being spread to maximum. Okay. So I'm not going to talk too much about a few last slides. There is a way we can get Bose-Einstein condensates, which just kind of evaporate all the hot atoms and let the atoms rethermalize. So this is how the temperature goes down. So like, you start with big and then you end up with the Bose-Einstein condensate. Then you can create different potentials to have it there and manipulate atoms in this typically light created potentials. Then you can have some kind of applications, right? For instance, atom interferometry. So this is something that I worked a lot, generally speaking, in the past few years, where we use Bose-Einstein condensates to use them like light, basically. You split them, you recombine them, you create interferometry. And this way you can measure different things, gravity, you can measure acceleration, rotation, and so on. And this field is very mature. We really work on characterizing the experiment, characterizing the fringes. And when it comes to atoms, atom interferometers, the thermal ones has been already been taken on airplanes to check them in extreme environments. So it's really mature technology. It's not BECs yet here, but this is just like the next step in the future. Perhaps this one in the background is going to be on the airplane one day. And I just wanted to give you a small demo. So there is a platform on the cloud that Quantum Science Center worked with, which allows you to create your own BCs, manipulate them, create kind of arbitrary space. It's called Octant. I don't know, have you had a chance to create an account for Octant? Okay, well, so I can quickly, I probably don't have time to do the demo.
Would recommend that we
Just move
pause
on.
for the break. And what I think will happen is many students may stay around during the break. And Kasia, if you want, we can certainly present the demo during the break itself.
Yeah.
But at this point, let's thank our speaker.